got here? Live. Does it say that we're on as far as
It takes a moment normally for it to pop up
okay.
on YouTube. It can there it is. We are up, and let me mute myself. There we go.
We're live. So all is good?
We are live.
All right. So hello everybody. We're going to be having a discussion about Polaris. I have Mike Van Graaff here, and we're going to be talking about Polaris, its position in the sky, where it is now, where it is in the past, or where it was, where it's claimed to be, where it could be in the future, and talk about some of the history of Polaris and some of the math to its motion in the sky. And so, Mike, if you want anything to add, otherwise we can get right into it.
Yeah, just to give people some background on who I am. I am a physicist. I am currently working as a physicist. I'm a postdoc. I got my PhD last year, and I'm working currently at Stanford University doing experimental physics. I am not an astrophysicist, but in preparation for this, I did some research and looked up some stuff, and there's actually been some wonderful developments in historical Polaris-related astronomy in just the last year or two, which is like as relevant as it could possibly be to exactly this conversation. So I'm really glad I was able to find that.
Excellent. Because yeah, what we're trying to establish here is basically that the thank you for the introduction. And he's a really nice guy. I don't think he said that in his intro as well. But, so basically, Polaris is the North Star, the pole star that we're going to be talking about. It's the star that when you look at a time lapse, you see that it does not move, or very small circle, and all the other stars appear to circle around it. And the claim is that there is drift to this pole star and that it will change over time. And so back in ancient cultures, a few thousand years ago, 4,000 years ago, like Egypt had said that the pole star was Thuban. And then right now it is Polaris. And then in the future, it is on its way to being Vega would be the next pole star. So the Earth essentially is for the globe cosmology is tilted at 23.4 degrees, and the Earth it rotates, but it also does something called precession, which means that it kind of wobbles like a top. And so if you spin a top, it'll stay upright as it's spinning, but then as it starts to slow down, it starts to loosen and wobble a little bit. And so the point.
The point, so it's always spinning. Yeah, exactly. A top is always spinning about, you've got the little handle and that makes a line down to the point, and it's always spinning about that, but that axis itself spins. So you've got this rapid motion around then, and then the axis of the top, it's precessing. So there's multiple different scales of the rotation.
Yes, and this precession, so if you were pointed at Polaris now and say it precesses 360 degrees and comes back to Polaris, that would be one cycle of precession. Yes. And to the globe cosmology, the convention is that it is 26,000 years of a precessional cycle. So if just hypothetically pointed at Polaris, and 26,000 years later, we would be back to the same spot pointing at Polaris. If you want to, maybe
I shared briefly. I felt like it very obviously. You should be able to see. This is just one of those time lapses you mentioned.
Do I click add to stream here?
Yeah. See, now it's there. And so this is actually a pretty short time lapse, but you can see that all those stars go around, and there's one bright star in the middle. It's not in the absolute middle, but it's real close. It's really close. And I think it's only like either 15 or 45 minutes of arc away. So the stars that star looks stationary, and all of the other stars rotate over the course of, this is probably less than an hour of time lapse. I don't know, but yeah.
Yeah.
So
But
and
that is
it's a super long exposure, which is why the tree still looks really bright, because even though it's at nighttime, they're just leaving the camera on.
Yeah, so they let a lot of light come in basically over a long period of time, and then it traces all the light that comes in as these stars are moving at 50 degrees an hour, roughly. You get the light that comes in as it's in one point, and then as it moves through the sky and gets to another point, it tracks the whole line, letting the light in, capturing these time lapses. And they are really a stunning
Yeah.
way to look at, time lapses of anything. Grass growing. Want to watch grass grow? Like, it actually in a time lapse like looks pretty cool. So
You can see things that you can't see otherwise, and if you do a time lapse of certain stuff, things turn invisible. If you do a time lapse, for example, or a very, very, very long exposure shot of just a roadway, the cars, if you see them, are vague blurs. If you just do it long enough, though, you don't even see the cars, because most of the time they're not there, and you're just looking at the road.
Like tail lights or something too, even.
Yeah, when the streaks, yeah, those like city shots at night, they're beautiful. Yeah.
Yeah, it's like looking into a whole other aspect of time, like something that we're like stepping out of our time perspectives, and then we're looking at it in like a sped up version. So yeah, this is a time lapse, and so this center star here is Polaris, and that is what we what we see the stars go around. And so maybe how should we go about this here, Mike? Maybe I could read off kind of.
Yeah, so the way this got started was, you can articulate sort of what knowledge you had, what people had observed in the past, that made you think that doesn't seem to match with the model that you just described, and you described it quite well. And that was sort of the genesis of the question, because you were basically like, I know that Polaris has been identified as the pole star for many, many hundreds of years, but if it's doing this precession over 26,000 years, 500 years is, it's a small fraction of 26,000, but it's not invisible fraction. Like, if this, it's rounded down to 25, it's 1/50th. It's 4%.
Yeah.
It's 2%.
2% of in over 500 years would be about 1.9%. 1.92 is what I got. So and yeah, so here let me so this is to show any flirs or anything or globes, like this is to try to show the globe side of the explanation of the precession of the axis based on historical context, because what I want to show here is like my mathematical reasoning for why something seems maybe askew with Polaris, and why it appears to be in place actually instead of askewed. So maybe what I'll do here is I
can stop sharing my screen, by the way. And you can you control that with like a panel at the bottom, I think. I've never actually done this.
Picture. How do I make it so that it's just my screen? Is this just me?
Yes, that's just you.
Okay. All right. So I'm gonna get my whiteboard here, and so basically, what we have is we have a globe with its axis, and it's pointed out at Polaris. And now the Earth is going to wobble and make this circle here. So you have Polaris and the circle. This is the precession circle, and this takes 26,000 years to make this circle. Now, if you take 26,000 and divide by 360, you get degrees. So every 26,000 years divided by 360 degrees, you actually get what comes down to 72 years. I think it's 72.2 years per 1 degree of precession. So every 72 years, we should get 1 degree of travel along this pathway because the Earth is preceding. So there's continuous motion.
Processing.
Yes. The Earth is precessing. So there's continuous motion as it drifts from one star, Polaris, to Vega, all the way back 2,400 or 2,200 years from now. It's at Thuban, like it was claimed to be with Egypt. And now we're back to Polaris 2,600 years later. So you have 72 years to get 1 degree. And then we have, so what I had seen with Polaris was that about 500 years, we'll just say for the sake of math, 500 years, Polaris has been at its spot with things going around it. And so 500 years out of the 2,600 years of the cycle means that for about 1.92% of the total cycle of the precession has been locked into Polaris. And here's the thing as well, is that in the globe, it is said that we are about 100 years away from reaching the peak, the apex, the pinnacle of being pointed directly at Polaris. Like our closest alignment will be in 100 years. So that would be a total of 600 years. And then if you figure going away from Polaris is the same, this could be up to, so you have 500 on one side, plus the 100 to get to the apex, plus the 100 to get back to where we are on this side of Polaris, plus 500 for the amount of time we've been stuck on Polaris on one side of the precession, and then 500 from the amount of time being stuck on the other. This would be about 1,200 years, or 12, this would be 1,200 years of a cycle, which should be about closer to 4% of the time. Times 2. So it's about 4% of the time we're stuck at Polaris. And in these 72 years, or in these 500 years that we've been pointed at Polaris, we have 72 years. There's 1 degree of movement along the circle. So just ignoring these 1,200, in 500 years, you have about 7 degrees is what I think it's like 6.9 degrees of total arc traveled. Okay, this is still. So if Polaris was here and Thuban was here and Vega was here, so you have Thuban, Polaris, and Vega. Now, whatever the angle is created here with theta, 10 degrees or 7 degrees, sorry, along the arc should be covered by the precession, by the wobble, because the wobble is a continuous.
Okay, I've identified where the issue is.
Yes. Okay.
So,
I'll click on your screen.
Yeah, sure. So you were for one thing, I want to go back and you said it was stuck. So the first time that I could see that was like on Wikipedia, and I sent you actually on YouTube, not on YouTube, on let me go to my sent thing. Do you mind if I share the email that I sent to you?
Yeah.
It's just the one I sent to you, so technically I don't have to ask permission for this one, I don't think. But let me just make sure there's no identifying information on here. There isn't. Okay.
Yeah, and I mean, some of my stuff is. But yeah, thank you for making sure it's. But yeah, go for it.
Yeah. Yeah. Okay. So here, I'm sharing the screen.
So I'll add to stream. There we go.
The first time that we know that people identified Polaris as the pole star was this dude whose name I can't remember, but it's on the Wikipedia page for Polaris, which I did link. It's there, and this is the sentence that this right here is something. It's in the. I don't speak the language, but Polaris is at 3 degrees and 8 minutes from the pole. 3 degrees and 8 minutes. That's what this apparently says. Now, I don't speak Italian and or Latin, whichever one this guy is writing in, but that's what it says. Today, if we go to Polaris today, and I share this tab instead, then we can look here and see the declination. The declination is 89 degrees, 15 minutes, and 51 seconds approximately of arc. A minute and a second. A minute is 1/60th of a degree, and a second is 1/60th of a minute. Mm-hmm. Makes sense. So that means that according to Wikipedia right now, which I don't know exactly when this was whatever, Polaris is 45 minutes, about 44 or 45 minutes away from true north. That's less than a degree. It's very close to being spot on true north. Now, let's round that to 0 and imagine that we're at the spot in the precession where it goes around and is processing like fully. Okay, so so this is the Earth, and this is the axis of rotation, and then like over here, for example, is Polaris, and then this is the equator, and this line here is the ecliptic. Do you know what the ecliptic is, Nathan?
Are you talking for the plane that we orbit about?
The plane in which we orbit the sun in typical cosmology is the ecliptic, and we are at an angle of 23.4 degrees. That angle there is 23.4. So, for one thing, now if you were to extend this line, that means that the angle, according to the Wikipedia page that we just saw, the angle of this triangle here, which is obviously difficult to draw to scale, so throw me a bone here. That angle, since right now that angle is 45 minutes or so, and back then that angle was 3 degrees and 8 minutes. That means that between then and now,
it's been almost
2 minutes, 2 degrees and 52 minutes. The position of Polaris relative to that fixed point that all the stars change around from when that guy wrote it down in that book that I just showed you to now, it has changed by almost 3 degrees.
So what he is saying is that how we see the rotational axis point at Polaris today, what he was seeing in the 1500s was that the point that the stars rotated around was actually 3 degrees away from Polaris. So Polaris actually would have rotated and made circles in a time lapse from back then.
And it still does today. It just makes a smaller circle. But for the record, the arc of the circle, it's smaller. The radius is smaller, but the arc is exactly the same for the record.
The arc is.
Yeah. And that is the
Degrees
angle
of travel.
that you need to be talking about, because so over 26,000 years, what is happening is that now the Earth, and for the record, the sun is like way, way, way over there. So I'm going to draw another Earth here, and it's going to point the other way, but it's still on the same side of the orbiting of the sun. I'm just doing it because, you know, I'm not going to draw it right on top of it. It'll get confusing.
Yeah. Okay.
So later we imagine, and now the Earth is going that way, and it's still spinning, you know, around, like here it's spinning like that. But it takes 26,000 years. But when the Earth receives the same point in its orbit, it is now, instead of pointing over here to where Polaris is, remember, this is just a shifted copy of this. Yep. It's now pointing over here.
Yeah.
Okay.
To Vega.
Which means that not after 26,000. This would be 13,000.
Yeah. After 13, yeah.
So roughly Vega. I don't know exactly how close it is, but let's just say that it's Vega, and so it's pointing over to Vega over here and over here. And so what you are saying, Nathan, is according to your logic and your calculation, because it takes 360 degrees for the thing to go around the entirety, you expect that from here to here, it's 180 degrees, right?
Yeah, give or take a degree or two for like ellipse.
The thing is, the circle that you need to imagine is a circle where you're here and you're looking up. And then what you have to do is draw a circle like that.
Yes. In the sky.
And then if you do that, let me go get a piece of paper. If you do that, okay, so it's tracing out a circle.
Yeah, it's like making where the point is of the axis is pointing is where it's at now, and then as it processes it, it creates that circle of
it creates that circle, and so from here to here, that is an angle of 180.
Yes,
but this angle only changes by 23.4 times 2. Because now instead of being 23.4 degrees this way, it's 23.4 degrees that way.
Yeah.
So the position of Polaris in the sky after it has traveled 180 degrees along its precessional path as viewed from Earth, and this is much smaller than it should be, but hopefully you can get it.
No, for visual,
Yeah. So that means that it will only have actually moved 23.4 times 2 is 46.8. So 46.8 is the maximum. If Polaris were exactly at the North Pole, then after 13,000 years, it would be 46.8 degrees, not 180. Did that make sense?
Yes. Yeah, that's what, yep.
And that is the number that you calculated when you said, okay, in 500 years, it should have moved that much. It did move that much. It moved that much along this circle, though.
Yes, that's the circle that I'm talking about, is that it should be 1 degree every 72 years of that circle.
And it has done that. It has done that. That 3.8 degrees, that 3 degrees and 8 minutes that was true in 1546 or so.
That's using a 180.
It rotated a little bit like this. So it around this circle that it's tracing out, it has done it's done about 2 degree.
Well, because that's
it's done 1/50th of 360 degrees, which is how many you did the calculation.
About 7 degrees.
It is, because it is 7 degrees, because then what you have to do is remember that you're not talking about just the position of the star. You're talking about
a section of the sky.
You're
Yes.
talking about a section like that, and when you go from here to here, that's 180. From here to here is 180, but measured from here, measured from my shoulder, it's only a change of like a few degrees.
Yeah. And to show here what he is kind of talking about is when we look at the sky, we have like a celestial dome. So we see this for our sky.
We have a celestial sphere, for the record.
Yeah, so yes. This is ignoring cosmology, but we see 180 degrees of the sky as we stand here. And so what he is talking about is when he says 3.8 degrees or 3 degrees in 8 minutes, he's talking about 3 degrees and 8 minutes of motion along this whole arc of the sky.
No, yes, I am. Yes, I am. Sorry. Yes, I am. You are correct.
And so, and then this circle here, well, it is 360 degrees itself for this circle. What this circle is not 180 degrees because it's only taking up, say at max, 46.8 degrees of sky. So this 360 degree circle is made within 46.8 degrees of our sky.
Yeah.
And so you have 3.8 degrees of motion along this, which now if you take that line there that I thickened up a little bit, I think you can see it. So now you take that line and you apply that to that same length to this arc, and you can see that 3.8 degrees here would be longer than 3.8 degrees along this 360 degree arc, or along this 360 degree circle. It's the same apparent position. So
it's two different numbers that are describing the same location. Yes. It's all about coordinate systems.
Yes. So that would be, so that then what that is saying that you have the 3.8 degrees of motion across our total sky that we see. When you put it into the precessional arc, that is going to translate to moving about 7 degrees along the arc of the North Pole's.
It's not that specific, because imagine imagine once again that that you're looking up at this and this is the North Pole. Okay? Oh, sorry, I realize you can't see it. So you're looking up and this spot here is the North Pole. Okay?
Okay.
What it's tracing a path like this, and when it's very near the North Pole, you're moving like directly away from it. But over here, your total distance from the North Pole, like here, when it's here versus when it's here, it's basically the same. The angle that you're going to see there is basically the same. So it's not a linear thing. It's not a linear thing. You have to actually do the trigonometry and be like, okay, this is the angle. I have to calculate sine and cosine and figure out exactly where it's going to be. So the two, they don't map onto each other directly. They do not map onto each other directly. It's kind of like if you imagine tracking a point along on a tire as it rolls down the road. The tire is moving at a constant angular velocity, but the distance of that point that you're looking at from the road does not vary at a constant angular velocity. It varies sinusoidally.
Yeah, it creates a sine wave.
Exactly.
As it goes up and down.
And so right now, because Polaris is very close to the like true north, we're in like the bottom of the sine wave, where that point is, for example, like really near to the ground.
Yes.
And then in 13,000 years, Vega will be at that point. But right now, Vega is like 46 degrees away.
So it would be like on the top of the sine wave.
Yeah.
Yeah,
exactly.
And that's what I was showing there with the two bars is basically it's apparent. Like you have the 180-degree sky's 3 degrees of arc, 3 degrees is going to be a lot bigger when you scale it to the smaller section, like of the sky that is the precessional area.
Yeah, but my point is you can't just do just a normal scaling. It depends on exactly where you are in the various relationship. I was just saying that you have to do like you got to do the math.
Yeah.
And it's physics. You have to speak. I am aware of one physicist in history who has like things named after him who was terrible at math, and that's Michael Faraday. Michael Faraday was actually just really bad at math, but he like was rich and had a lot of magnets or something, so he was able to discover Faraday's law.
Yeah. Create the cage and everything.
Yeah, and honestly, we say he was bad at math. He was probably just bad at math compared to the other physicists. He was probably fine at math. Right. People like to say Einstein was bad at math. Einstein was better at math than anybody you and I have ever met.
Yeah, he did a lot of math. Okay.
So this is what's happening is you have gotten the fact that it moves 180 degrees on this circle.
Yep.
Which is a cone sort of thing. You were thinking, okay, I can do math. 26,000 years, 360 degrees. That's a certain number of degrees. It's 72, and that's correct. That's a number. If you Google and you look up like on Wikipedia like axial precession, you're going to see something. I think it's about like 72 degrees, and that's the precession of that angle.
Yep.
So
of the wobble.
Of the wobble. But imagine for example that the Earth, that instead of it being tilted at 23.4 degrees, imagine if it was tilted at 1 degree. It's still doing 360 degrees, but around a really, really, really narrow cone. Mm-hmm. So that was where I think the geometry can very easily become confusing. And while I was looking at this,
because you don't want to confuse taking the whole sky when you're looking at a sample of that sky.
Yeah, you need to know.
So any measurement when you translate it back out to the bigger sky is going to be a smaller number.
Yeah, so you need to know where the center is of your angle.
Yeah, if you measure that 7 degrees in this smaller section, if you measure that 7 degrees, which is a bigger angle in a smaller section of sky, when you then look out to the bigger sky, you have to shrink that angle because that angle that took up a bigger space in the smaller measure is going to take up a smaller space in the bigger measure. It can't hold 7 degrees of arc across a small circle is not going to be the same as 7 degrees of arc across a bigger circle.
Yes.
So that's why there has to be a changing of the value.
Yes.
Yeah.
So while I was doing the research for this, I found I was able to find that thing that I showed you where it was written in the Italian, and it's that's great. I also was able to find this awesome new paper. So this is a new this is a paper from the Journal for the History of Astronomy, and this came out last year. Okay? And it's about, they found this document that is a copy of Hipparchus's star catalog. Hipparchus was an ancient Greek astronomer from around 128 BC. And he wrote some stuff, and particularly the famous astronomer Ptolemy used a lot of this stuff. And they found this document, and what this document is it's a palmacet that somebody in I don't know, like the year 600, something like that. It probably says right up here. I don't know, but I haven't looked. Somebody said, oh, they found this old thing where somebody had done their astronomy homework on. And they were like, this is stupid. I don't care about this. They washed off the ink as well as they could, and then they wrote some religious texts upon it. So what you see, thank you. What you see is the religious text, but underneath it, you see the eraser marks of the previous text. And they can figure it out, and they can read it. By the way, this is also basically how we have everything that we have from Archimedes is the same way, because monks did a lot of erasing of old non-Christian texts, and then they wrote over it with Christian text. So, yeah. And so it says all of that. And here's like the translation, and it gives all of these measurements. And in particular, it gives, for example, here, these are measurements of alpha Yumi is what I will call this. Yumi stands for Ursa Minor. Polaris is the very tail star in the constellation Ursa Minor. As such, it has been recorded, and at that point in time, according to Hipparchus, in 128 BC, instead of being 3 degrees and 8 minutes away, as it was in the 1540s, or instead of being 45 minutes away, as it is today, back then, he recorded it as being 12 degrees and 24 minutes away.
Yeah.
That's a lot. That's a lot. You're not going to think of that as the North Star. That's not going to be useful for navigation. It's not going to be as useful as the North Star is for navigation.
No.
That
would create a fairly large circle relative to what Polaris is making today.
Polaris is helpful because Polaris, you don't need to know what time of night it is. You just see Polaris and you're like, that's north to within as good an accuracy as I need. It's super convenient. But generally speaking, it's not that hard to know what time of night it is, particularly if the moon is visible and you knew where the moon was last night and you are used to keeping track of these things because you're an ancient mariner, you know you're going to be able to figure out where you are. As long as you haven't moved. There's a problem with longitude, and that wasn't solved until like the 15 or 1600s because they had to invent really good clocks. Different discussion. But my point is that this was not the North Star. They wouldn't have called this the North Star, and they didn't call this the North Star back then. It was significantly further away. Now, this is actually worth keeping in mind because right now, in the last 500 years, it changed from 3.8 to it changed. That's not 0.8. It's changed from
to 45. Isn't 45?
Yeah, 3.1 to like 45 minutes. So I wish they would just use decimals instead of minutes.
Right. Hexadecimal.
But if you divide that by 500 years for the past like 500 years, and then you do 3 degrees and then you do 12 degrees and 24 minutes minus 3 degrees in that, and you divide that by 1600 years, you're not going to get exactly the same thing. Because you're actually going to notice that in the last 500 years, it's moved faster because what it's doing is it's moving directly away or directly toward in the last 500 years. It's basically moving directly towards the pole, whereas back then it was sort of going at a kind of an angle.
So if you want to, are you saying that it's making, if it's speeding up towards Polaris, that means that it's making more of a direct approach towards it? So this wouldn't be a circle that we're talking about. We would be talking about something that's more of an ellipse.
It is still a circle. My point is, if this is your reference point and you're going in a circle like this at a constant pace, when you're here, your direct velocity with respect to that point is faster than if you're here. Even though your motion is still in constant, you're always going around this. You're going at a constant speed, not velocity, speed around this sort of circle. But when you're in this vicinity, you're going to be approaching it, and basically all of your motion is either directly towards it or directly away from it. Whereas over here, your motion is just parallel to it, so your distance from it doesn't change.
Yes, because for that moment where you're on the other side of the circle, you are essentially at a balance point. You're equal to it on the other side of the circle.
Yeah, if you were to measure just your distance from that one reference point, you're at an extremum on that curve.
So if it's a circle, if it's a circle and you are traveling 1 degree along this circle every 72 years, why is it faster in the last 500 years of going along the circle as opposed to any other segment of the 500 years, like 3,000 years ago or 4,000 years ago? Like, why would it be slower now or faster now towards Polaris than back then?
So let's break it down. Break it down.
Break it down. Hey, Michael, do you mind if I just ask you, have you ever heard of the Georgia Guidestones?
Yes, vaguely, not for a long time.
Okay.
I would say that that's probably so. My understanding is that they are stones that lie along lines that seem remarkable. There's like a pattern there that seems. Is that sort of it? That
could be. I was just talking in reference to the Georgia Guidestones they were destroyed last summer. But they were like people say like the 10 commandments of the NWO for like how to manage human population and nature and everything like that. But why I wanted to bring them up was because they had in the Georgia Guidestones, they had a hole that was drilled through it that you could look up at Polaris, and it was the North Star, and it was a really small hole, and they were up for about 40 years, and so you could see that this whole time, which is about it would be half a degree of this arc circle, but it was at that point. That was just some as a modern structure.
Yeah, but let me tell you. I bet you money that if you got a well indicated photograph that where you had your camera at exactly the same spot now as you did 50 years ago at the same time of night at the same time of year, you'd be able to see the difference in where Polaris is. You would.
Wow. Okay.
I'm saying it moved several degrees in the last. The size of the moon is half a degree. Okay.
Yep.
If you have a well indicated thing and these things don't move, and you take the same measurement every night, which is how they did it back then. They have measurements that they specify to 1 minute of arc. That's you have to design a thing that lets you look to do that. You can't just eyeball that.
With a scale to measure it at that.
Exactly.
Because you have to be able to take that fine measurement. The eye can't discern and resolve things at that small of an angular size.
Not in a way that you can like give it. You can compare two objects. If you compare an object that's this big and an object that's that big, I can tell you that one's bigger than the other, but I can't tell you how big they are.
Like a quarter and a dime, if you have them.
Yeah, exactly. But if I hold a dime out at a distance, how big is it? I actually don't really know. I know it's probably about a degree-ish, but I could be off by a factor of 2.
Yeah,
exactly.
Completely
relative.
Smaller.
Exactly. So if you want to tell me that it was always in the same position, I'm going to want data and I'm going to want two photographs taken on the same time of day at the same time of year, assuming that that's the correct thing, which I
sounds like relative sky speaking. The sky is in the same position.
Yeah.
50 years later, all the bodies and everything in the same spot.
Yeah. Because stars do move. And there's another thing that I actually did want to bring up, which is called proper motion. But first, let's finish this thought. So you were asking, why does it seem like we would speed up in the last 500 years?
Yeah.
So in the last 500 years, imagine that, again, so this is all a view that only has, from the perspective of Earth, from sort of here to here, except it's along this axis. Yep. This is 46.8 degrees.
Yeah, of our sky that we're looking at.
Yeah, we're looking at a cone, and it's going like that. So in the last 500 years, Polaris went from being, and if this, imagine this right here is true north.
Okay.
That's where Polaris is right now. And this was where Polaris was 500 years ago.
Yep. Okay.
Okay. So it's traveled this amount, and all of that motion has basically been almost exactly towards the north, right?
Yeah. Okay.
So over those 500 years, it has moved 3 degrees in the sky, and it has also moved 3 degrees with respect to the North Pole.
Yeah.
Now let's imagine we come back in 13,000 years, and so that was this. That was 500 years, starting from 500 years ago, and then today. Now, instead, 13,000 years later, we're watching it go from here to here over 500 years.
Mm-hmm.
The distance from the North Pole has basically not changed, though.
Well, isn't it talking about the distance you travel along the arc of the circle? Like if the circle,
that's not the one I'm talking about. Right now, I'm talking about why the distance wouldn't seem to change too much. This angle is the same. This angle is the same. Yes. That angle is the same. But,
and the amount
what you're saying is it seems like. But you were asking, why does it seem like it's getting closer faster? Because and when you're asking that question, what you're asking is, why does this distance change fast now, but on the other side of the orbit, this distance doesn't seem to change fast? And I think that this explains it. It's the same thing about the tire. And
wait, so you're not saying that it's getting, because you said that if it was 3 degrees in 500 years, and then if you worked it back to the 12 degrees 2,000 years ago, that it wouldn't exactly scale.
It wouldn't, because this is an extreme example. So the difference is that my point is that from here to here, it's very subtle. It's very subtle, but you would notice the difference. Like if you just did how much this distance changed over 1,500 or 1,600 years, you're going to get some angles per year, and and you shouldn't do that because that's changing. My whole point is that is changing.
Always get 72 degrees a year. Like if
you're measuring from here, you do always get it. If you're measuring from here,
yes, from the center, you always get 72 years for 1 degree.
But the way we measure it is we point a thing at the sky, and we do one of these star chart things, and we let it trace out. And those stars, all of those stars are moving about this point. So we're talking about different circles.
Okay. Hold on. So you're talking about the red dot would be where when we observe a time lapse photo, we are looking at the red dot.
Yes, that is the North Pole. That is the North Pole. And Polaris is near there, but it is not there. It is very near, but it is not there.
But why does the circle that's rotating our pole star, why does that have any regard for the center, for where true north is? Like, why does where our Earth is wobbling out an arc across the sky have any?
It
Why would
doesn't.
the north?
It doesn't particularly.
It just happens to be that they're lined up this close to each other.
Well, they're 23.4 degrees away from each other.
Can be.
What you're saying, what you're asking is why is this angle what it is? That's actually what you're asking. And that angle, again, you have to view from Earth, and that angle is 23.4 degrees.
Well, it's like as you're going, if you were, say you're on if you start at that center dot, the green dot, and you go to the left where you're at the black dot next to the red dot, and then you go down to that green dot just below it. If you're at that green dot, why does the circle path that you're on, whether it's bringing you closer to the pulse, to the true north, or away from it, why do you care what direction you're going relative to that star if you're going in your constant motion along the circle where every 72 years you're traveling 1 degree?
I don't understand the question.
Like, why does the star, if the measurements are that we would get a speeding up apparent, like we're covering more ground.
I shouldn't have said it that way. I regret saying it that way. When I said that, what I meant was if you were to calculate the apparent distance over many years. This is not something that happens in one night. This is not something that happens if you were to track you do in one night, you do a long-term exposure of the sky and you figure out where it's rotating around. Okay. Right now, that's there.
Okay.
It's rotating around there, very near Polaris.
Okay.
In 13,000 years, now that point, and maybe I should have done it this way originally. That point, it's better to think of that point as moving to over here than it is to maybe think of the stars as moving over there. The Earth instead of rotating like that, now the Earth is rotating like that. And it takes 13,000 years for that to happen. It's very slow, and the reason it happens is because we're getting tugged on mostly by Jupiter. Jupiter.
It is a constant, and it is
mostly. There's even a little bit. There's even a little wiggle here that goes at 13 point. That takes like 18.6 years, but it only has an amplitude of like 9 minutes of arc, and that's caused by the moon.
So that would be very
slight. Very slight. Yes.
Okay.
We can measure it now because we're really good at measuring stuff, and we have photos, and we can, you build a big telescope. That telescope doesn't move much, and if it does move, it's moving by, like, the way you figure that out is by well, I guess you don't believe in GPS, but you can measure tectonic plate movement. So. Yeah.
And I think that there's legitimate measurements that are made with that technology. But, like, let me see if I can. So what I guess what I'm trying to ask is something like, okay, so if you have a circle, and then we're looking at a certain section of that circle, and so say it creates like an arc like this, and each one of these dashes is 1 degree. So 1 degree, 2 degree, 3 degree. And so regardless of what star is here or what star is here, these stars are going to make the same continuous motion of every 1 degree every 72 years. So if it took to get from here to here, this is 3 degrees and 8 seconds, 3 degrees and 8 minutes in 500 years. And then to get from here to here, it's 12 minus 3. It's about 9 degrees in 1500. Like that to me looks scalar.
So they are pretty similar. Those are pretty similar. We would need to do the precise numbers.
Okay, that would make sense. Because that could be
so for the record, I'm willing to do that. Given our time, I can, but I would be more likely to make mistakes doing it live. Last time we talked, I did a lot of math live, so you know I'm willing to.
You're good, dude. You do another math. We can do another part to this. What did you want to get to about
proper motion?
Proper motion.
This is what I wanted to get to. Yeah, let me pull it up. Oh, well, not pull it up. So, well, yeah, there's one thing I want to pull up. So, do you know what proper motion of a star is?
No. Could you explain it? Well, I think I've heard it. I know I've heard the term, but you can just explain it.
Yeah. So imagine, so in mainstream cosmology, there's a lot of stuff in the sky. Some of it is like really, really, really crazy far away, right? It's like nuts far away.
Yes.
So when you're out like driving when you were a kid and your parents or whoever was driving you, and you're in the car and you're looking out like the mountains that you're driving by, if you're driving by mountains, those are like sort of barely moving, but like the power poles right next to the road that are going,
they look a lot faster, which would be parallax.
That is parallax. That is parallax. So in astronomy, parallax is like when on here, and then 6 months later we're on the other side and we see a thing. But the other thing is, what if your car was parked, but you still had, for example, and then you were watching another car drive along? That car is going to look like it's moving with respect to a very, very distant object.
Yes.
That is so the apparent motion of a thing in the sky, a star, the apparent motion that we see compared to the stuff that's like infinitely far away. The stuff that's infinitely far away doesn't move. We can't measure it. We're always getting better, so that that distance, how far away things have to be before we can't measure they're moving anymore, always gets further and further and further away. But there's a lot of stuff that it could be moving at the speed of light.
So far away that the parallax speed that they travel makes them look motionless.
Yeah. So proper motion. Let me share my screen. Share screen. Just don't show these tips. I don't need to show you. So yeah, proper motion is the astrometric measure of the observed changes in the apparent places according to the abstract background of like infinitely distant stars. Okay? So this, for example, this is the money shot that I wanted to show you. This is Bernard's star. This is a star. This is not a planet. This is a star.
Okay.
And those are years.
Yes.
And what I'm saying is that this is a star. It's a very close star to Earth. It's not the closest, but it's one of the closest. It's only like 5 years away because Bernard's star is, how far away? It's 6 light years away. Okay? It's the 4th closest star compared to the triple system of Alpha Centauri. And compared to these much more distant stars, this star is moving, and it's moving fast.
So this star,
my point is that this makes total sense in my model, and there's just no reason for any of this to happen in your model, which you don't have. Also,
yeah, okay. Well, so I guess I have a question of looking at this. this star, Bernard's star, is in our galaxy, right?
Yeah. It's six light. It's one of the closest. It is the either
It's a
fifth or
neighbor. It's in
fourth
our local
closest
group.
star, depending on if you count the sun.
Okay, yeah.
It's super close.
Yeah. So
Yeah.
if it's rotating with our galaxy and our whole galaxy is all rotating along at one speed, why does this star? How did this star like speed up out beyond its?
They're not. The galaxies are
revenue?
not rotating at one speed. They're not rotating at just one speed. You have a typical expected velocity, but that's sort of like saying if a so in a gas of molecules, you're going to have a particular velocity distribution.
Okay.
There's going to be a most likely velocity. There's going to be an average velocity. There's going to be all of these things. The average velocity for just a box of a gas of atoms, the average velocity is 0. The average speed is almost the speed of sound.
Wow,
you need to be very careful about exactly what you're talking about.
Well, so does that mean that
the galaxy is not a rigid object? The galaxy is a whole bunch of things that are all independently obeying, the laws of gravity and motion.
So there could be a band of somewhere that is close to the center of the galaxy that is going, say, fast, and another band close to the center that's going slow. And then in the outer rings of the galaxy or all the outer arms of the galaxy, you could have some fast moving particle or some fast moving objects and some slow moving objects.
Yeah. Just like it's just like in the solar system. Like, yes, if you know enough about its orbit, you're going to be able to predict like where it's going in the future. But there's a lot of things that could we could throw we could throw a sports car into outer space if we wanted to. And somebody has done that, believe it or not.
Yeah, Elon.
Elon did that.
But
I know you don't. But
I mean, if he did though. I mean,
you're my project. Like, Nathan, straight up, you're a little bit of a project for me right now. I'm going to be honest about that.
That's cool. I'm getting experimented on by people that I give consent to. I wouldn't consent to, people unforcefully.
I'm not experimenting on you. I'm just trying to convince
look at it
you.
as an experiment.
Yeah.
But no, and I get it. I mean, I get that. But I also I'm fine with you trying to convince me. But I also why I particularly with you, Mike, is what I like is you to explain things, because how you and I had talked before that we went live here, you were saying you have to know your opposing models to be able to formulate arguments and critique them and try to properly falsify them. And so for any flurfers out there, to better understand the workings of the globe and how it says the sky looks and everything, because it is helpful to know the positions and to accurately. So I don't think anyone wants to be wrong. If there's anyone in the flat earth or globe community that knows that they're wrong and deliberately wants to be for whatever reason, that's on them. But I think lies are terrible for humanity.
Lies and mistakes are different, though.
Yes, they are, and there's a difference. There's a difference between a lie and a mistake. But to people,
you are absolutely. I think that you're very confident that I am not lying to you. But you're also pretty confident that, at least when it comes to me saying that the Earth is round, that I am wrong.
It would be a misunderstanding of, but I would, you are by no, you're not
exactly.
Exactly. I would say wrong or misinformed, as you would say to me.
Yeah.
But I am also not lying to you. There's no.
Absolutely.
We're just trying to help flesh out understandings of how things are working, because someone who is trying to go after the globe, for example, and has some uniform model of rotating galaxy that doesn't help if the claim is that the galaxy has bands that can move at different speeds and different orbits.
That is true. There's this whole thing, spiral galaxies. The argument that you're making seems like it was going towards these spiral galaxies should just wind up and you shouldn't be able to see the spirals anymore. Is that an argument that you're familiar with?
I've never heard that. No.
Okay, that's a common one because people know that things that are closer to the center of a galaxy, they should be orbiting faster, and the things way far away should be orbiting slower. And yeah, that's going to turn, if it's just a bar, it's going to turn it into a spiral, but eventually it's just going to wash out the spiral and it's just going to look like a disk. This is a very common argument. It doesn't work because that's not what's happening. What's happening is this thing called Lindblad resonances. Lindblad resonances are basically density profiles that emerge as a natural consequence of when you just have a whole lot of things independently sort of like kind of rotating. They end up self-organizing into these spiral arms that are density waves. It's like a traffic jam.
So one star doesn't have any concern about how another star is moving.
Yeah.
It's doing its own thing.
Exactly.
Excluding like space-time.
Yeah, excluding like gravity. Yeah, excluding. Gravity. I mean, it's moving to the gravity, but
yeah. Okay.
Yeah.
That might actually be a good time to stop. I did have a couple of questions about maybe that's something we could do, like dimension and size of the galaxy, because that's like, say the galaxy
actually have a topic. I have a specific topic that I would like to cover. So you and I were discussing in a recent video you did, and I have not watched the one you released today, but I'm sure I will. But you released a video, I think last Sunday. Do you tend to come out with one video a Sunday? Is that like
I've been trying to get with work and vacations and stuff. I have to, my schedule at work is not the most stable right now, but I want to try to put out like a video a week, at least, maybe two, depending on when I can get like a Sunday off, or if it's Tuesday or Thursday during the day, or during like a Friday during free time or something, if I can find it. It's but yeah, I'm trying to, I want to be consistent in like uploading.
There was one thing that I wanted to oh man, where is it? Let me try and find it really quick. Absolute. Is it? Oh no. Right. Give me 2 seconds here.
You good?
What I'm looking for a paper. And the paper, that was weird. The paper that I'm looking at is about gravity measurements. Here
so what are you doing right now? You're pulling up what we can have be our next topic.
Yeah, I'm pulling up a thing that I want to be like our next topic.
Yeah. So this will
and yeah. So let me pull this up. So here it is. Let me go and share my screen now. So I mentioned this in our comment conversation on your not most recent, which you came out with earlier today, but your last video before that, I think. And I'd love to discuss this with you. Absolute airborne gravimetry. There's like 8 different versions of this word with a cold atom sensor. Now, I am a cold atom physicist, so and I use atom interferometry, which is exactly what this uses. So this is very much exactly in my wheelhouse. And what this paper, they flew a gravity measurement thing over Iceland. And they flew it back and forth, and they measured how strong the gravity is. This is the raw data, which is very noisy because there's a lot of vibration on the plane. But then they filter it, and they use this way of filtering it. And then these are all of the different, calculations for, in particular, the Eta-Voss effect. This is a thing that I would very much want to discuss, the Eta-Voss effect.
Yeah, we can.
And so what they notice is that how how fast things fell depended on where they were. And here, this line, they went from going east to going west, or from going west to going east, rather. And the force of gravity got weaker.
Yeah, this would be because the Eötvös effect is basically saying that when you travel in one direction, and that would be a visual graph demonstration of as you travel in one direction, things can weigh less than going in another direction where they weigh more.
Yes, and this is, as far as I cannot think of a single way that this does not demonstrate that the Earth is round and that the Earth is rotating. This is a proof of that, as far as I am concerned. And also, not just that, not just did it fluctuate depending on which direction they were going, it fluctuated depending on where over the island they were. And it depended, if they were over a mountain has a lot of mass, and gravity was stronger there. But over a valley, gravity was weaker.
So this object on the plane, this what was being weighed, it was an atom. It was weighing more as it was flown over a mountain.
It was accelerating downward more.
Same
thing. Those are two different ways of saying the same thing, but yes.
For precision, yeah, okay.
Yeah, and
accelerating
this,
more over a mountain, creating
exactly.
a greater weight reading on the measurement device.
Yeah, because the extra mass from the mountain is causing a little bit of extra gravity. And this, I did not know about this paper until I was looking it up like a week ago. In preparation for this and also other stuff.
Would you want to send me that and we can?
Yeah, I put it. I sent it as a, well, okay, maybe YouTube might have eaten it because I put it in the comment, but it occurs to me that YouTube probably doesn't like people putting links in comments. But yes, I will send you.
Yeah, I don't know how to. Is there a comment section in our stream?
Not this one. It was the previous one where you and I had the back and forth about observation and constancy. Which, by the way,
okay,
I have thoughts about that. But
well, we can we can maybe wrap things up here, and then if you want,
I want to talk about this. I want to talk about this paper.
Yes, we will talk about this. This will be a preview of of the third topic that we cover, which will be the Eötvös effect.
I don't know how to pronounce it either.
We're just the Eötvös effect, which talks about the weight of objects going west or east. And if you want to address in that next video too, we can talk to about observing and whatnot. Do you want to close out at all with anything should we close out here?
Yeah,
are you cool with that?
Yeah.
Thank you, Mike, for being here too. Thank you a lot for them. This is hopefully really instructive and helpful for people, myself included. So I'd never heard about the galaxy bands of different rotational speeds and everything. So I did my in my PhD program, there are a lot of different things that you have to go through, and one of the stages of my comprehensive exams, the second stage of it, I had to write like a long 20-page review article. This wasn't published in a topic that was not my area of expertise. And then I had to give a presentation on it, and I had to defend. They interrogate you to make sure that you actually learned this topic, and they ask you hard questions. And quality education right there.
Yeah. And so it's sort of like it's the single most stressful part of the PhD, because in my program, and this is typical nowadays, your thesis defense. If there's a concern that you wouldn't pass your thesis defense, then your advisor should not let you go through with it. If you are doing your thesis defense, that means that there is a 99.9% chance that they are going to say, "Congratulations, Dr. Van de Graaff. at the end of it. Because if you're not ready, then they shouldn't be letting you get up there.
Correct.
Sometimes they mess that up. I asked one of my professors, and he said that he had seen one defense where the student was just simply not prepared, and he had to come back again and do it 6 months later. And it was super
unfortunate for him.
But the topic that I did was migration of planets, of protoplanets in a gaseous protoplanetary disk. So like when the solar system is forming, and a lot of the same physics that shows up in galaxy formation is relevant to that problem. So
like the solar system is almost like a microcosm of a galaxy.
A little bit.
Planets become stars if you go from solar to galaxy, in a way.
In a way
of looking at it. So
dark matter is really important in galaxies, and it's not in solar systems as far as I know. So that would be one difference. Just the amount of time is another difference. But I mean, and you know us. Well, we always like to just to go and be like, oh, like give it a few billion years, it'll be fine.
Add some time to it. Okay.
Yeah, I think I'm all set. I'm really looking forward to our next conversation. I love these. These are like the highlights.
Dude, it's so much fun.
I have such a good time doing these.
Yeah, it's a great time, and I really thank you for the time, Mike, and for everything. And yeah, next time we will cover the Jovotus effect.
That's how I pronounce it.
that got into a little bit of French gibberish there, so no slang or nothing.
I don't even know what language it is. I think
yeah. So all right, thank you very much, everybody. Mike, you as well. Thank you kindly. Hope y'all are well. Peace be with you all.